Hi, everybody, and welcome to today's session of the Spectral Geometry in the Clouds seminar. Today, we have the pleasure of hosting Genqian Liu from Beijing Institute of Technology, who is going to talk to us about geometric invariance of spectrum of the Navier-Lame operator. As usual, if you have questions during the talk, you can either ask them in the chat and I will relay them, or you can unmute yourself and ask them directly. So for the next hour, the floor is yours, Genqian.
Thank you. It's my pleasure to give this talk at Spectral Geometry in the Clouds. I would like to thank Professor Nagic and Professor Alexandra Gerard for your invitation. In this talk, I'm going to discuss geometry invariants of spectral of Navier-Lame operator. There are 6 parts in my talk. Why is Navier-Lame operator? Background and non-facts, main results, key ideas and methods, simple expression of resolvent operator, asymptotic expression. Let's look Navier-Lame operator. This is a Navier-Lame operator. Delta is Laplacian and Laplace is a gradient. Navier-Lame operator is a linear elliptic differential operator of second order. Here, tau and mu are Lame parameters, and tau and tau plus mu are positive constant. P plus and P minus denotes Navier-Lame operators with Dirichlet and Neumann boundary conditions. P plus is a Neumann boundary condition, and P minus is a Dirichlet boundary condition. Associate Navier-Lame operator, we have elastic eigenvalue problem. In this eigenvalue problem, on the left side, this Navier-Lame operator, and lambda is eigenvalue. And while there is a lambda k and uk satisfy this problem, the spectral is non-negative, discrete, and unbounded. And lambda k increase and tends to inflate. This is elastic wave equation. In 3 dimensions, the elastic wave equation describes propagation of a wave in isotropic homogeneous elastic medium. Most solid material are elastic, so Navier-Lame operator describes such phenomena as a seismic wave in the Earth. Equivalent, we can derive Navier-Lame elastic wave equation in this form. In this form, if the second term set to 0, then Navier-Lame elastic wave equation became Maxwell equations. In addition, if mu tends to minus tau, the Navier-Lame elastic wave equation become a classical wave equation. The second section, we give some background and non-facts. Wave equation, this is a wave equation. This is a Maxwell equation. E electric field and H is magnetic field. The third equation is Stokes equation. U is a velocity and P a pressure. This is an incompressible condition. The last equation is Navier-Lame equations. Here, this is Navier-Lame operate, and this is Navier-Lame wave equation. Associated above 4 equations, we have 4 eigenvalue problems. The first eigenvalue problem is a Laplacian dirichlet eigenvalue problem. In this problem, mu is eigenvalue problem. This mu is eigenvalue. And on the boundary condition, we have a dirichlet boundary condition. The second eigenvalue problem is an electromagnetic eigenvalue problem. But in this eigenvalue problem, we have different boundary condition. The boundary condition is a mu time E. That is, the E is a problem to the boundary. The third eigenvalue problem is a Stokes eigenvalue problem. Mu is a velocity and P is a pressure. Laplacian lambda is an eigenvalue. The boundary condition is a dirichlet boundary condition. Here, mu is a positive constant. That is kilometer coefficients of Wisconsin. The last eigenvalue problem is elastic eigenvalue problem. The left side is Navier-Lame operate, and the lambda is eigenvalue. The boundary condition is dirichlet boundary condition. What is the relationship between the spectrum and geometry for the elastic Navier-Lame operate? What is the geometry invariance of a spectrum for the Navier-Lame operate? This is a very important problem. Let's look at some history and background. This is a dirichlet eigenvalue problem. Mu1, mu2, and mu p dirichlet eigenvalue. In 1910, H.A. Lorentz conjecture for a two-dimensional domain that follows asymptotic expansion holds. On the left side, this is a counting function, and on the right, this is a geometry quartet. Lorentz conjecture was proved in 1913 by Hermann Weyl. This is asymptotic law imply volume omega is a spectral invariant. In 1954, Planck showed the follows asymptotic expansion. In this expansion, the left is about eigenvalue. Mu k is a dirichlet eigenvalue. And the right of the right side, this is 3 terms. The first term about volume of the domain, and the second term is about volume of boundary omega. This is the third one. Third one is a constant. Katz also conjecture for R hold the number 1/6 should be related 1/6 1 minus I. McCain and C in 1967 in a celebrated paper in Journal Differential Geometry in 1967 gave a affirmative answer to the conjecture of case. This is McCain and C asymptotic expansion. On the left, this eigenvalue quantity. On the right side, this is a geometry quantity. The first term about surface volume of omega. Second term about curvature integral. K is a scalar vector. The third term about constant, the constant dependent domain. For dimension 2, the formula is this form. The left is eigenvalue, and right side is a geometry quantity. The first one is about area of this domain. A second one is about Euler characteristic, and the third one is about scalar square integral. This is a second formula. Let's denote Laplacian minus. Laplacian minus is Laplacian of the direction boundary condition. Laplacian plus is Laplacian on the Newman boundary condition. Then McCain and Siegel gave this formula. The formula on the formula left here side, this is about eigenvalue quantity. On the right, this is a geometry quantity. The first one is a volume of omega. The second one is about surface area of part about the bound domain. The second term is a curvature integral. The last one is about boundary. In the boundary, the mean curvature. McCain and Siegel also gave more information about curvature of the boundary. Genqian explained, calculate more coefficients of expansion of trees of height color by pursued operator theorem. Let's look at the Maxwell equation. This is a Maxwell equation. A Maxwell equation, another form. Balanson, Gretchen, Hessler gave this theorem. The theory is state lets omega domain with compact, closed, and smooth boundary consist of n components of a general G1, G2, and Gm. Then we have this formula. The formula is about eigenvalue. Left side is eigenvalue, and right is a geometry quantity. In the asymptotic expansion, A0 is about this quantity. Zy is 0. A2, A3, and A4 give explicit. In 2021, I gave this theorem. The theorem about Stokes eigenvalue. Let omega be a bounded domain with a smooth boundary, and let lambda 1, lambda 2, lambda k eigenvalue of Stokes operate. Then we have this asymptotic expression. On the left, it is about eigenvalue. Lambda k is Stokes eigenvalue. On the right side, this geometry quantity. The first term is about volume of omega, and the second term is about boundary volume of boundary omega. This remain as t tends to 0. Let me give a remark. This is a potent theory because it is difficult to prove this result. Today we will give a main result. PG is a Navier-Lame operator or Riemann manifold given by this representation. Here, this is a Bouchner Laplacian. This is a Bouchner Laplacian. This is a rich curvature. We have this theorem. Let omega be a compact Riemann manifold of dimension n with smooth boundary omega, and let tau 1, tau 2, tau k minus is a directional eigenvalue. Respectively is a tau 1, tau 2, tau 3, and tau k plus is a Riemann boundary condition. Now we have this formula as a asymptotic expression. On the left side, we have this quantity. This quantity is about eigenvalue. Tau k plus or tau k minus is a Navier-Lame operator with Navier-Lame eigenvalue with directional boundary condition or Riemann boundary condition. On the right side, we have two terms. The first term, this is a constant about dependent t, and this is a volume omega. The second term is about boundary value of a boundary. This is a constant dependent t and lambda or mu. This is our main theorem.
Sorry, I want to ask a question.
Okay, very good.
So we studied this problem in our book. There is a book, Safarov and Vasilyev book. We have a section devoted to this problem. We did not study the heat expansion. We studied the counting function, the Weil coefficients, but these things are expressed through one another. So we have the first two coefficients in our book. I can email you my book.
Yes, you're right. In this asymptotic expression, we have a two term. You write, if we give this first term, you can get the one law.
Yeah, but we have two terms. We have two terms in our book, two. And we were not the first ones to do it. The first one to do it was Larson Sager, a famous theoretical physicist in 1960. He got the first two coefficients in dimension 3. For dimension 3, and free boundary, he got the second coefficient. And we refer to him in our book. In our book, we give the second coefficients for dimensions 2 and 3. I will email you my book. It has also references to Ansager's 1960 paper. But I also have another question. I'm sorry that I keep coming up with questions. I do not understand how you can impose Neumann boundary conditions for the elasticity operator. The free boundary condition is not the Neumann boundary condition. You write down the potential energy and you vary it. And this gives you the free boundary condition, the physically meaningful condition. Yes. And it's not the Neumann boundary condition, it's more complicated. So maybe you can consider the Neumann boundary condition. I'm just pointing out that it's not physically meaningful for the elasticity operator.
Yes, you're right. For the duration boundary condition is correct, but for the Neumann boundary condition is different. You may be use another Neumann boundary condition, that is drvu mu plus lambda u and type mu. That is another Neumann boundary condition.
Okay, I don't remember the precise form of the free boundary condition for elasticity. It's rather complicated. It's expressed via the stress tensor, but it's obtained by variation of the energy function. That's all I wanted to say.
Yeah. Thank you.
Okay, thank you.
Thank you. From this theorem, I give an answer to the interesting open problem matched by I.G. Evermead. Evermead proposed this open problem in 2006. How to prove this theorem? I give key ideas and method. For PG plus or minus, this is a Navier-Lame operator with dirichlet or Neumann boundary condition. From this operator, we can get or we can generate parabolic semigroup. From this semigroup, give initial WO, we can get W plus or W minus T or X. This function solve this parabolic equations. The part is Navier-Lame operator. This is a parabolic equation. The boundary condition is a dirichlet boundary condition. The second equation is about parabolic equation. The boundary condition is a Neumann boundary condition. From W0, we can get W minus or W plus Tx. Solve these two parabolic equation. From this parabolic equation, we can get a fundamental solution for the parabolic equation. This is a KTXY fundamental solution. But this solution we can get this Y. Fundamental solution we can representation by this form. UK is normalized eigenvector and lambda k is eigenvalue. This is a famous representation about fundamental solution. From this representation, we get this quantity by take trace and integral. The right, by take trace and integrate, we get this term. On the left hand side, we take trace and integrate, we get this one. On the other hand, we can construct a heat fundamental solution, or we can get heat cloud from this formula. This formula is a quotient integral formula. C is a suitable curve in complex plane in positive direct right spectral of P plus or P minus. From this quantity, we can get asymptotic expression. Let's say this is left, this is right. Right is about eigenvalue, left is about fundamental solution. From this fundamental solution, we give from this formula, we can get expression. This is the first term, a second term, a third term, and so on. As t tends to 0, we can give explicit is A0, AY. A0 is a constant depend t, tau, and mu. This is a value of a boundary domain. The second one is AY. This is a constant depend t and Lame parameter, and this factor is a value of a boundary omega. This main ideas and method. How to calculate this y? This is a PG. It is a pursued operate. We can represent pursued operator by this formula. This is a symbol of PG. We denote tau identity minus AG equals 3 term. The first one is the symbol of degree 2. The second one is a symbol of degree 1, and this is a symbol of degree 0. We can write A2, A1, and 0 very easy. A2 have this expression. This guy is AY. A2, this is A2 matrix. This AY matrix. This is A0 matrix. The purpose of calculators resolvent about lambda I minus A. This is resolvent. How to calculate the result of the trace? If G is an identity metric, we have this quantity. The second result is a trace minus 2x q tau is this quantity. How to prove this lemma? It is important note that this matrix and time this matrix equals to this matrix and time quantity. This is a function. Scalar function is important. Observe about this fact. We can get this set generate a matrix array. That is this identity matrix. This is GY, GN, GI. That is this matrix. From this matrix and this matrix, we get a matrix array by addition and multiplication. We get this phi F is a matrix array. From this matrix array, we can get A2 minus Y equals S, Y identity plus S2 this matrix. This is important observation. From this expression, we can get A2 times A2 minus is identity. This A2, this is A2 minus Y equals identity. From this quantity, we get these equations, matrix equations. That is, we get these two equations. From these equations, we get S1 and S2 substituted to S1 and S2, we get Q minus 2 equals to this quantity. This is a matrix. That is, we get Q minus 2, the first principle. From this principle, we get trace. Trace is this function about matrix. The last section we give asymptotic expansion. First, we from this omega and omega star. What is omega star? That is a double. We from this domain and this domain, we close two domain. We get closed domain. The coefficient about Navier-Lame operate, we can get a parabolic equation. This is a parabolic equation. From this parabolic equation, we get a fundamental solution KTXY. KTXY in the closed Riemann manifold, the fundamental solution is a good fundamental solution because it belongs to CY and C infinity. From KXY, we can get K minus and K plus. K minus is a KTXY minus KTXY XY star. Minus plus is, this is a plus. This this kxy is a fundamental solution with dirichlet boundary condition. Now, from this k plus and k minus, we get ktx. We have this expression. This is a symbol, and this is a Cauchy integral. This is a integral on the Rn. The ktx x star is expression. This principal et tau. This is integral, Cauchy integral. We have this ktxx and tkx star. It follows from calculus this integral, we get this quantity, and hence we get this result. In integral domain, we have this quantity. This is a constant depend t, and this factor is a value of omega. Let's give a set. The set is u epsilon partial omega. The partial omega is a partial omega neighborhood. In out of this neighborhood, we have this expression. Expression is this quantity. Integral, this quantity we get, this is OT minus 2 n over 2 as t tends to 0. Finally, in neighborhood, we calculate this integral. This integral in the neighborhood about this quantity we can get. This is a boundary omega. This is x. This is x star. We can get this matrix test of the neighborhood. Now, about result, we get this integral equals this quantity. That is on the neighborhood, by calculate the integral, we can get this quantity. This quantity about value of omega. It follows from about two quantity equality. We can get the integral w and omega equals to this quantity. This quantity have two terms. The first term is a value omega in the omega, w of the omega. The second one is about boundary. From this integral, we get our result. That is this integral, we divide two terms. The first term is equals to this quantity, and the second term we can get this term. From this two term we get our result. we complete our proof. From this theorem, we can get a corollary 1.2. That is, omega is a bounded domain with a smooth boundary. Suppose Navier-Lame spectrum with directional boundary condition is equal to eigenvalue of BR above of a radius, then the domain is equal to BR. How to prove the corollary 1.2? In order to this corollary, we just use asymmetric inequality. This is asymmetric equality. From this equality, from partial omega and partial by, this quantity equals this quantity, and b omega value omega equals to br volume. We can get omega equals br. We get our result. Remark 6.1. By applying Taubry theorem for the first term on right side, we can get Weyl-type law for Navier-Lame eigenvalues. This is a counter function for the Navier-Lame operator. On the right, we get this quantity about, this is a constant, this is 8 tends to inflate. Let me point as mu tends to minus tau, the Navier-Lame operator reduced to classical Laplacian. There, our result recover all correspond result for Laplacian by let tau tends to minus mu tends to minus tau. The follows reference. I give some references.
Thank you very much for this talk.
Thank you.
We have time for questions and comments if people have some. I think someone wrote something in the chat. Look. Well, if someone wants to add something or ask a question.
Alexander, could I ask a question, Michael?
Yes, go ahead, Michael.
I wrote something in the chat, but I'll repeat it. There are two questions. Firstly, for Neumann conditions as understood in this talk, I'm not even sure they're self-adjoint. It doesn't follow from anything I know that they're self-adjoint. Secondly, I'm amazed that the final theorem gives the same answer for Dirichlet and Neumann. The second term is a different order operator. It can't be that the asymptotics, two-term asymptotics is the same.
This two is different. The first is a minus for this is our result. For eigenvalue or Navier-Lame operate with direction eigenvalue, it is a minus k tau k minus. And the second one is a minus.
Yes, but
if we get Newman eigenvalue, that is a plus. We get the second term is a plus. This is a different.
Yeah, but the last theorem you showed, the very last theorem.
Last theorem. Oh,
Yeah, the last slide.
You're going in the wrong direction right now.
No, the last, not the first. Before literature.
This one? This one?
At
No,
the
no.
end of the file.
At the end, before literature.
Literature.
Before literature.
Before literature.
At the very end.
Very end. This one?
Oh, no, probably further. It was page 57, 50 something.
50. Let me see. This one?
Yes.
Oh.
There is no plus or minus. It's the same formula.
Yeah. Because I get two terms, I just take first term. I can get.
Oh, okay. It's a
well,
first term. Okay, for first term, I agree.
From first, we can get this Y-type law.
Yeah. For one term, I agree. Okay. Yeah, thank you. But yes, still,
maybe
the question remains why your Neumann condition is self-adjoint. It's not clear why your Neumann condition, it's very non-classical. Why is it self-adjoint?
Oh, maybe. Maybe you're right. Let me think later.
Okay.
You're right. That is for first term, we can get Y-type law. That is for durational alignment is the same in my remark.
Yes, but your Neumann is very unusual.
Maybe you're right. Maybe it is a different. Maybe it's the same. Let's think it late. Thank you.
Okay.
Could you give me your email? We can.
Yeah, sure.
Okay, thank you.
I will send it in the chat.
Oh, thank you.
Thank you, Michael, for the question. And are there any other comments or questions? Please go ahead. We have time.
Professor Liu?
Yeah.
Can you hear me?
Yeah.
I have a question. What are the main difficulties or obstacles in computation of these spectral invariants?
Pardon?
And what are the main difficulties or obstacles in computation of these spectral invariants?
You ask about Stokes eigenvalue theorem.
The question was what was the main difficulty in the computation of these?
What are the main difficulties?
Yeah. Thank you. The main difficulty, we have two difficulties. The first difficulty is calculate symbol. Also, you must calculate the symbol of Navier-Lame operator. This is very difficult. For example, if we want to calculate the first principal symbol, we can use about 10 pages. But if we get the two-term symbol, we can use several double pages. It's very difficult. This is the first difficulty. A second difficulty is about boundary. We how to deal with boundary, because if the domain is a closed domain, that is no difficult. If we get false, but for the domain with dirichlet boundary condition or Newman boundary condition, we must use another technique. For example, we must use a double the of domain, and from close many Riemann manifold, we can get the second or third or fourth term. It is very difficult.
Okay, I see. Is it sensitive for the regularity of the boundary?
See.
If the boundary is not smooth, will it be?
Yeah, you ask about no smooth boundary.
Yeah.
Yeah, maybe it is difficult, but I can't do this thing because I must give a transmission to the boundary to self space. That I must transmit boundary to half space, Euclid space. We can get the boundary result.
Okay, I see. And I have another question. What information of the manifold does the third spectral invariant contain? And
what?
What information of the manifold does the third spectral invariant contain?
Oh, even I calculate the third term, but it's difficult. I and my PhD student spent a lot of time calculate the third term, but it's long, very, very difficult. The result is very long. For example, if we get a third term, we must use many technique and result about 10 or 20 pages. Difficult. I'm sorry,
Okay.
I can't get the result about the third term.
Okay, I see. Thank you.
Thank you very much. Does anyone else have a comment or question? If not, I propose that we thank our speaker again. Thank you very much.
Thank you. Thank you.
And we will see each other next week at the same time for a talk by Maciek Dworski, who will speak about spectral theory of internal waves in fluids. Thank you very much, everyone. Have a great week. Take care.
Thank you for
Thank
the
you.
talk today.
Thank you for the talk.